I have a quarter and a magnet, and a paper clip contains iron, which is a ferromagnetic material that is strongly attracted to a magnet. I also have a piece of aluminum here. Now, aluminum is a paramagnetic material, so it's very weakly attracted to a magnet. In fact, so weakly that I cannot pick up this magnet. So essentially we think of aluminum as non-magnetic. This piece of aluminum is about 1 meter long, and I have it leaning against the wall, and the base is about 15 centimeters from the wall. I've taped a piece of pink paper against the quarter so that it can be readily visible against the piece of aluminum. So if I put it against the aluminum and let it go, it falls rapidly, as you would expect, because of the force of gravity. Now, I've taped a piece of blue paper to the magnet, and remember, the magnet was not attracted to the aluminum, so you would expect the same thing, that the magnet would fall rapidly. But what we see is that it falls fairly slowly. As the magnet is falling, the region it enters, there is now a magnetic field, and the region it's leaving, the magnetic field is disappearing. From Faraday's law, we know a changing magnetic field will induce an electric field. And if that electric field is occurring in a metal, it will induce currents. And if it's a plate like this, we refer to those as eddy currents. Now, we can use Lenz's law to qualitatively understand the direction of those eddy currents. And Lenz's law tells us the direction of current induced in a conductor by a changing magnetic field will be such that it will create a magnetic field that opposes the change that produced it. As the magnet is sliding down, let's assume the North Pole is facing the aluminum. So in the region in front of the magnet, there will be an increase in magnetic flux into the aluminum. So there will be an induced magnetic field to oppose that, and so eddy currents will start to flow in a counterclockwise direction. So remember, put the fingers of your right hand in the direction of the current flow, and your thumb will point in the direction of the magnetic field. So that will be a magnetic field coming out of the aluminum. And it will be like a North Pole pointing out. Now, in the region where the magnet is leaving, the loss of magnetic field will be opposed by currents flowing clockwise. So those will induce currents will generate a magnetic field into the aluminum. So again, if you put the fingers of your right hand in the direction of the current flow, your thumb points in the direction of the magnetic field. And so in this case, there will be a south pole pointing out. Okay, so as the magnet slides, in front of the magnet there's a north pole being induced, so it would repel the sliding magnet. And in the region it's leaving, there's a south pole pointing out, which will pull on the magnet. So that's why the magnet slides slowly. It's because of the induced eddy currents. Viewing it from the side, we have the magnet that's sliding down the aluminum, and so the induced magnetic field in front of it is such that it's setting up a magnetic field like this second magnet here. So their north poles are opposing, and behind it the induced magnetic field is like this, where there's a south pole attracting the falling magnet. A place where you maybe experienced an application of this magnetic braking is a roller coaster. So in modern roller coasters, the way they stop them at the end is with this magnetic braking.